Okay, our next container is going to be called a stack. And one difference between some containers is how the items are ordered and how they can be accessed. So we say a stack is a last in, first out container. Okay, and what that means is if I were to add things into a stack in this order, let's say 1, 2, and 3, the only way to retrieve them is to pull them back out in this order. 3, 2, and 1. So notice the last thing that was inserted is always the first thing that comes out. And the name stack comes from a spring-loaded tray holder in a cafeteria. We've probably all seen these where they're kind of this big box, and if you want a tray, you'd always have to grab it from the top, and then another one just pops up, right? So you can grab your tray, and then the next person will get the next one. And then if you're like a cafeteria worker and you're cleaning these trays, you'd put them back on the top. Okay, so all inserts and retrievals are done at the top of the stack. There's no ability to remove from the middle. You have to work from the top. So we use stacks actually all the time in programming. A stack is used to control the flow in our programs. So if we were to look at this code here, we have a main function that calls foo, foo calls bar, bar calls zip. Okay. Well, in order for the system to kind of remember where to jump back to, we have this thing called a call stack. Okay. Okay. And if we're in a function, let's say we're in the main function, we have this thing called a stack frame available to us. So if we're going to declare any variables, they go in this spot here, any local variables. Okay, let's say in main we're calling foo. Okay, so what happens whenever we call a function is we create a new stack frame. And the first thing we do is we store the address in main to return to. Right, so if foo is called here on line 12, well, we're going to store that address on this stack frame. And then the flow of control is going to jump into foo, and we declare this local variable x. So there's going to be some room set aside in this stack frame for the variable x. And then we have this other function called bar. That means we're going to add a stack frame. We're going to store an address, the address in foo to return to. Okay. Okay. And then the flow of control obviously goes to bar. And then here we declare two variables, local variables y and z. Those would also go on that stack frame. And then we call zip. So again, the whole thing's going to happen again. We'll create a stack frame. We have to store the address in bar, where to jump back to. Okay, the flow of control is going to jump inside here. Here there's not any variables, local variables declared, but whenever we pass a parameter by value, that's very much like a local variable, where num is going to hold a copy of, in this case, z, that came from the bar function. And then this is our call stack. So we started in main, and then we were in foo, and then bar, and zip. Now, eventually we're going to get to the end of zip, right? The ending curly brace. What that means is we're going to pop the call stack to get the return address and remove any local variables. In this case, the parameter num was our only local variable. Okay, so we always have the top of the stack, TOS, and right now the top of the stack is here. So we're going to pop this to get the address and bar of where to jump back to, right, which is right here. And then we're going to literally get rid of that stack frame, and now our top of the stack is here. Eventually we're going to get to the end of the bar function, right, and we're going to pop the call stack to get the address inside foo of where to jump back to. and we're going to get rid of y and z. Those are the local variables. So any local variable is accessible from the point of its declaration until the ending curly brace of the block it was declared in, because these stack frames are going to go away. They're going to disappear. They're going to be popped from the stack. And the flow control will return back here to foo. And eventually we're going to come to the end of the foo function. That means we're going to get the address in main of where to jump back to. Going to get rid of x, and we're going to jump back, okay, to main. And eventually we're going to get to the end of main. And of course that's where our program ends, but if we were to continue on this path, that means we would get rid of that stack frame as well. Okay, so that's kind of how a stack works in general. You kind of put things on top of the stack, and when you want to remove things, you remove them from the top of the stack. Now the stack data type will have an interface that looks like this. Okay, the way we add something to a stack is we call the push function. And we're going to push an element. And the reason I made this a const t reference, const so that the element can't change. When we're pushing something onto a container, it shouldn't be able to change. But we still want to pass by reference. That saves us from having to, make a copy of the data. Okay, so we get the benefit of pass by reference, and we're sure that the piece of data can't change inside that function. Okay, then we have this function called pop. This is how you remove something from the top of the stack. So we fill in the element with whatever value is at the top of the stack, and then we remove it. Now top is kind of similar to pop in that it returns the element of the top of the stack, but it actually does not remove it from the container. So top is like what we would get if we did call pop and remove. And then lastly, there's an isEmpty. Okay, so here's how one might use a stack. So let's start here. We have this stack called S, and initially this is totally empty. Okay, and then when we call push and we push the value 10. Our stack would look like this. And when we push again, okay, we're pushing 12. 12 would go on the top of the stack. Okay. And when we push a 2, 2 will be on the top of the stack. And then lastly, when we push the value 5, it starts out with these 3 values. And then we'll add the value 5. Okay, so all pushing happens at the top of the stack. Okay. Now next we might want to start popping. Okay, so pop again says remove from the stack. Okay, so if we were to call this first pop here, x would be set equal to whatever's in the top of the stack. Right now it's 5. And then our last element would be removed. And our stack would look like this. It would have 3 elements in it. Okay. Our next call to pop, again, x would be equal to 2, and our stack would have 2 elements in it. Okay. Our next call to pop, x is going to get filled with the value 12, and we'll have exactly 1 element inside the stack. And then our last call to pop, x will hold the value 10, and our stack will now be empty. Okay, so we pushed 4 times and we popped 4 times. Now let's talk about different ways of implementing a stack. It turns out a linked list is a really good way to implement a stack. You might recall from our discussion of linked lists that all new items get added at the head of the linked list. Okay, so if we had a linked list and we were going to insert 10, 12, 2, and 5, right, remember our linked list starts out empty, so head points to nothing. Right, but if we do an insert, right, we create this new item, we set the data, we set the new node's link to point to whatever the head points to, null, and then we make the head point to the new node. And if we continue to do this, right, so this says kind of create a new node, store the data, make the new node's link point to whatever the head was pointing to. So the head was pointing to the node with 10. And then lastly, make the head point to the new node. So we'd have 2, followed by 12, followed by 10. And then lastly, when we insert 5, head will point to the node with 5, 5 will point to 2, 2 will point to 12, and 12 will point to 10, and of course 10's next is null. Okay, then if we wanted to remove from the list, we could remove from the front of the list, right? And again, that would be as simple as saying go to what the head points to, right? Grab that piece of data, but then delete that piece of data and adjust the head. So then it would be 2, 12, 10. If we called remove again, we could return that piece of data, delete this node, and adjust the head to point to the next one. Okay, we could do another remove, get rid of the node, and make the head point here. And then one last call to remove. Okay, we would eventually make the head point to null. Okay, so we could insert by inserting at the head, a new node at the head, and we could remove in a linked list by just removing whatever the head points to. So if we had a linked list that could do those two things, it'd be really easy to create a stack. Right. We would just create a stack which as a data member has a linked list. Of course we'd fill in the type T in the stack. And then we could add our push method to the stack class, right? And all we would really do is insert into the linked list. That's going to put the element at the head of the list. And when we do a pop, well, all we'd have to do is remove from the front, right? Remove whatever the head is pointing to. Okay, so this is a very good strategy to create a stack if you have a linked list that supports inserting at the head and removing from the head. Okay, so unless you have a good reason not to do this, that's how I would create just about any stack that I wanted to create. I'd use a linked list. Okay, but I do mention that there's another way to create a stack, maybe using an array-based container. So there are some extreme situations where you might not want to rely on the heap. First of all, not every environment supports the heap. Some environments are so rudimentary that they don't even provide a heap. So here I'm talking about small and expensive embedded devices. For example, like a thermostat or a digital watch. Yes, you can program it, but it doesn't have a real sophisticated operating system. So in those cases, you might not have a heap space to work with. You might have to work without a heap. And then there are these other types of applications that have these things called real-time requirements. You might have heard the term real-time. Real-time does not mean real fast. A real-time requirement is just one that has a deadline. And if you miss the deadline, it's as bad as the requirement not being fulfilled. So for example, suppose that we have some software that controls the wings of an airplane. And the pilot requires that the wing reacts to the movements within, let's say, 200 milliseconds. Now, if our software works, but it takes 5 seconds for the software to react to the pilot's wishes, so it works, but it takes a 5-second delay instead of 200 milliseconds, and the plane then crashes into a mountain because the software didn't react in time. It still reacted, but the 5-second delay meant the pilot couldn't get over the mountain. Well, yes, the wings moved. The wings did what they were supposed to do, but they didn't meet the deadline, and this is as bad as not moving the wings at all. Right? Everyone is still dead. So this is an example of a real-time requirement where the deadline is important as what needs to be done. Now, in the old days, pizza places would guarantee delivery of pizza in like 30 minutes or less. That's, again, a real-time requirement. If the pizza wasn't delivered on time, they lost the money from the sale. So missing that real-time requirement was actually worse than not having the customer at all, because you still had to deliver the pizza and give them the pizza if you were late. Not many systems have real-time requirements like this, but some do. And these systems, again, tend not to look like the laptops and desktops that we use every day. Instead, they might be, in medical devices and military equipment and things like that. Usually on a desktop, there's no penalty for a delay in opening a Word document. We might not be happy to wait, but if the program eventually opens, we will wait a few seconds, right, without much complaining. That's not true in a real-time requirement. The deadline is very important. So my question is, well, how long does it take to allocate a node on the heap? Well, there's a memory manager that must look through the entire heap space to find a chunk of memory that's both large enough to satisfy the request and is free. And it's hard to say exactly how long that's going to take. If our heap space is littered with chunks of data that are being used, it might take a certain amount of time to go and find a chunk that's both free and big enough to satisfy our request. So for real-time systems, this unknown amount of time it takes to allocate memory on the heap may cause us to miss a real-time requirement, and that would be very bad. Okay, therefore there are some times when we wouldn't want to use a heap-based linked list to implement a stack. Instead, we'd want to use an array-based stack. Okay, so we can do that. We can kind of declare an array and say that we are going to use the memory in this array to put things in a last in, first out order. Right, so let's say we had our array we made big enough to store those 4 items. Okay. And we could say, well, the top of the stack will maybe always be position 0. Right. So, okay, we're going to push 10. But then when we want to push 12, right, if the top of the stack is always supposed to be the very first item, we'd have to take that value 10 and move it over to make room for the 12. And then when we wanted to add the next item, 2, right, well, first we have to move the 10 over, then move the 12 over to make room for the 2. Okay. And then lastly, to add that value 5, first we have to move the 10, then the 12, then the 2 to make room for the 5. Okay, so there's clearly something wrong here. Moving all the elements every time we want to add one item is inefficient. Now, pushing onto a stack becomes a big O of n operation. And the larger the stack, the more inefficient this becomes, the worse it becomes. We would like push to be a big O of 1 operation, a constant time operation. So we can still do that with an array, but we have to change our idea of the top of the stack. Okay, so what we're going to do is we're going to have a special index called the top of the stack, and we're going to always store the next element in that index. Okay, so basically the way this is going to work is we're going to have same array with 4 elements. Okay. But we're also going to have this variable called the top of the stack. And we're going to initialize it to maybe the value -1. And basically what it means to push is we're going to add 1 to the top of the stack index and then store the element at that position. To pop, we're going to return whatever's at the top of the stack and then decrement the top of the stack variable by 1. And to look at just the top, we're going to return whatever's at the top of the stack and not do anything to the top of stack variable. Okay, so our array would start out kind of looking like this, and then when we said push the value 10, we're going to increase this value by 1, and then we're going to go to the array at that position and store the element there. So top of stack right now is really referring to this thing at position 0. Then when we push 12, that means we're going to increase the top of the stack variable by 1. We're going to go to the array at position 1 and store the value 12 there. Now the top of the stack is really referring to this chunk. Next we're going to push the value 2. That means we increase the top of the stack. We go to the array at that position, and that's where we're going to store that. So now top of stack refers to position 2. And lastly, when we push the value 5, we're going to increase this variable to 3. We're going to go to the array at position 3 and store our value there. And the top of the stack refers to this chunk here. Now when we call pop, remember pop is going to return the piece of data at the top of stack index and then decrement the index by 1. Okay, so we've just pushed 10, 12, 2, and 5, and our top of stack is over here. If I call pop, what we're going to do is we're going to return that value 5, and then we're going to decrement the top of the stack to make it 2. Okay, so now top of stack is here. Okay. Then if we call pop again, we're going to return this value 2 and then decrement the top of the stack from 2 to 1. And 1 is the index of this value here. If we call pop again, we're going to return 12 and decrement this to 0. And then lastly, when we call pop one last time, we will return the value 10 and then decrement the top of the stack. Now it'll be -1. And that's how you know when you have an empty array-based stack. If the top of stack index is ever equal to -1, well then we know the stack is empty. Now an array-based stack would either be, you'd either pass in a chunk of memory to be used for the array, or maybe you could create the array in the constructor, kind of like a one-time only operation, and then manipulate it with these stack methods that we talked about. Now an interesting thing can happen with the stack. If it's array-based, it can become full. So we might want to have an isFull method that would be added to the interface. And if we tried to push onto a full stack, we'd want to throw an exception. And similarly, if we ever tried to pop from an empty stack, I think that warrants an exception being thrown as well.